right, good morning. My apologies for the delay, but it didn't take that long to get up and running. My internet kept cutting out, so I didn't really have a choice but to risk a restart, but it was much smoother than that other time, which was over a month ago, I guess. All right, so if you look at the schedule, especially this week, make sure you look at the schedule and see what is happening every day. Tomorrow's a holiday. Things are a little different this week. Yesterday's task was to go through a self-paced session with a video that was already in the playlist on modular arithmetic, where we are essentially taking the number line. That's not a very pretty number line. Let's make a straight line. That's much better. That continues forever, of course. And we have 0 and 1 and 2 and 3, 4, and all the integers. Over here, we have our negative integers, and so on. And then we essentially wrap it around over here. And if we look at the familiar clock, let's suppose we have to make a decision. We wrap it around. 0 is always going to be at the top, and we wrap it around until 12 wraps and sits right at 0. Now, we could have chosen something other than 12, of course, but just to make it a little bit more familiar, we usually start with our clock, but as we discussed in that video, it can be anything, right? And then we call this the mod 12 circle, or mod 12 numbers, or whatever. So it's important to realize a couple of things, that if I look at my number line model and I do, for example, 2 plus 3, number line model said stand at the first number, look according to the operation addition in this case, and take 3 steps forward relative to where I was looking. And then I get to 5. Here everything is the same. I am still going to, if I look at 2 plus 3, for example, I'm still going to stand, I'll stand sideways and look to the bigger direction and take 3 steps. However, if I stand over here and let's say, we'll still say it's still at 5, mod 12. So in some cases, there's no difference at all. But if I, for example, say 11 plus 2, now on the number line, if I look here, 11, 12, and 13, there are infinitely many numbers, infinitely many positions, and I'll never run out of steps that I can take with new positions to reach. But if I stand at 11, look to add, this clockwise direction is still the making bigger direction I want to walk in. Take 2 steps. I now sort of looped back on myself and I'm back at 1. So even though, the number line is wrapped around itself over and over and over on the circle. And behind 1, there is a bunch of numbers. There is 13, there is 25, and so on, infinitely many. It just wraps around the circle. 1 is, in a sense, the representative of all of those numbers, and they're all in the same class, we say, the same modulo class. But so technically all the numbers, all the positions are still there, but the only answers that I can have are the representatives for that position. So I can still do 11 plus 2 in the number line way and get 13, but there's no 13 on the circle. It's hidden behind its representative. So I then say this is 1, and I specify because I'm counting on a mod 12 circle. This is not equal in the same way as the others, as the number line arithmetic was, because this is more of a class that it's equivalent to. So we put a little extra line there. And we call that a congruency. But if you want to write an equal to make yourself feel better, totally fine. You just have to say which circle you are on. And that justifies why it's not 13. Because I'm counting on a different kind of line, a line that's connected to itself in the circular way. So there's a lot of similarities between the number line and the modulo whatever circle. The problem is my answer, my final answer, is can only be one of these representatives. So I don't want to rehash all of that. It's all in the video. You probably watched it already. It was yesterday. And if you didn't, then maybe wait for the backup of this video, wait for the recording and watch that first. Otherwise, it might be a little confusing. Okay, so we've done all that. We did addition, subtraction, multiplication even, and saw how the number line and the mod circles are the same and how they're different a little bit as well. Okay, so today isn't supposed to be a repetition of that. We'll move on to something that is often neglected in terms of how we're thinking and what we're really doing. And this is a good opportunity to sort of highlight an issue that I find. So when we think about teaching and learning, there are different levels. When I'm introducing something, a concept, at a very low grade, I'm going to do that in a very specific way. Even though there exists a deeper understanding behind that superficial introduction. So think about integers. Now my experience is kind of limited, so you'll have to take my word on some of this. But if I introduce just positive integers with a number line, and the addition and subtraction that we did using the number line method, for example, we never took mathematical shortcuts. We never simplified anything. We just walked around the number line or used the chips as you want. So on the very left of this, what I call on the understanding spectrum, on the very left, I have a basic intuitive understanding of how things work. I'm keeping my examples simple. Let's say I use small numbers, simple examples, to make things manageable as a first introduction, often used for an introduction purposes. That's all on the left. And whether I'm learning something, it should be with those key concepts in mind. It's basic, it's intuitive, it's easy to understand and get a hold of. The examples are simple, the numbers are small. It's my introduction. Whether I'm teaching it or learning, I'm going to start on this left side. But if you think about just addition, just think about basic integer addition. The number line method is going to become quite inefficient and tedious if I have large numbers I have to add. If I have to add 573 plus 221, do you really still want to go to the number line, tick off this position 573, look, and then step 221 steps to the right? No, right? It's not. I'm past my introduction. I'm shifting towards more efficient, more sophisticated methods relative to where I started. So then we have our addition method. We don't walk around on the number line anymore. We use the decimal properties of our number system and come up with a systematic recipe, a stepwise procedure to find the answer. That's beyond walking around on the number line, because we have a more sophisticated understanding of how numbers, integers specifically in this case, in this example, work. So as I'm done with my introduction, I shift towards, let's say, deeper mathematical understanding. That could mean many things, of course. Properties of the decimal system that allow me to come up with a method and not walk on the number line anymore. Let's say here, sophisticated, oopsie, probably need to learn how to spell it. Sophisticated, or more sophisticated, it's all relative, right? More sophisticated properties or methods, and there are multiple levels here, and in the case of integers and number theory, it really never ends. So there's never an end line here, really. It depends on my needs, depends on what's efficient and effective for my purposes and my situation. Sort of the size of the numbers and the issue guides how fancy do I need to get. Now, it's very important that I am super comfortable on this left side, because that's where I'm going to start. Grade 1, I do not step away from this left basic side. As the numbers get bigger, I have to be comfortable to take at least a few steps to the right and understand some properties, understand and at least have a glimpse of how things work when it's not quite as simple anymore. So often, what is connected to these, we're going to take a specific example with our modular arithmetic to illustrate this. It's just one example of many. And when we get to fractions, we're going to come back to this actually. What often happens in the background here, on the left side, we very much have an inductive reasoning approach to everything. We're exploring certain properties, maybe just by way of example. And it's very important as a teacher to understand more so that I can set up those examples to guide students to the correct conclusion. Because we know that inductive reasoning has a little bit of a risky side, that if I just blindly look at examples, they might lead me to an incorrect conclusion in general. So it's important from a teaching perspective that I do know how things actually work, at least a few steps to the right here on this line, so that my examples that I set up lead the students to what I know is the correct conclusion, regardless of the topic. So when I shift over to a more general mathematical understanding of how everything is connected and how things work and whatever the issue may be, I am going to have to shift over to a deductive reasoning view, let's call it, because I have to step away from my specific examples to be sure how things actually work in general. Okay. So I'm not saying be a pro at number theory. I'm certainly not, because there is no end to this subject. It is extremely complicated. The more steps you take, the more steps there are to the right. We just want to understand one step. Just take a step away so that what you're teaching isn't all you know. You need to know a little more, just a little, in order to set up examples to guide students in the right direction. It's very important to know more than what you are teaching. Just a little, but still more. Okay, so I'll make 2 pages here, one for the left side, and I'll sort of have an, oopsie, zoom to 33 is a nice size. I'll sort of have our example based approach, or of course inductive reasoning, right? Those go hand in hand. And then I'll make another page. This isn't quite the way we're doing it in the book. I think this might actually be better. So general, I'll just say we have a general exploration, and in order to make general statements, whoopsie, speaking and writing, 2 different things, do not go well together. Our deductive reasoning is kind of needed to make general statements, right? So we have our left side of the spectrum, and then for us just one step in to see how do you confirm things in general outside of specific numbers. And I'm going to take a specific example based on our current topic. So now let's look at, let's keep the circle at 12. Why not? Let's just see it over here. Make our mod 12 circle. I have to always do it in pieces so it's nice and balanced. 4 and 5. It, of course, can be any circle. This is now our example based, right? So I have a specific example, and I work within that example. So let's note some things. Let's make some observations, some examples. Let's take, for example, I want to have something that pushes me over, perhaps. Let's say I start with 9. Yeah, that's fine. And I add 4 to get to, on the circle, I'm going to get to 1, 2, 3, 4, 1. Mod 12. I have to emphasize the circle I'm working in. If I focus on my starting position and my ending position, I can notice that there are 2 ways to get there. One is adding 4, taking 4 steps in the plus direction, let's call it. But the other way is taking 8 steps in the minus direction. So 9 minus 8 is also going to give me 1, like it does on the number line. So it'll definitely do that. I have the space. I don't loop over 0, even on the circle. My circle's big enough. So I have 2 ways of getting from my starting position to my end position. Let's take another example. Let me just erase these circles, right? Let's take a different starting position and a different ending position. Someone is not muted. If you need to ask a question in the future, just let me know in the chat, because I don't think you can now unmute yourself. I might forget to do it, so just let me know in the chat if you do want to ask a question. Okay, let's take a different position. Let's take it doesn't even have to be, let's take 4 and 10, why not? Let's suppose I start at 4. Of course, I'm going to add 6 and I get to 10, even on this circle. But if I want to start at 4, I can also subtract 6. Sometimes it's the same because I'm right on the other end of the circle, right? The other side of the circle. And I'll get to 10 as well. Okay, so again, same starting position, same end position. I can add something and subtract something, and that something can be the same. Let's do one more. Where should we start? Let's go with, I don't know, 7, and let's say we want to get to 10 again. I can add 3 to get to 10, or I can subtract 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. And I'll also get to 10. Now I know if you are a little bit stickler for such things, I shouldn't write an equal sign here, but I find that it makes people a little more comfortable. As long as you have the specific circle you are counting on attached to that equation, it's okay. So for any number, these are just 3 examples, right? There are many more, and the circle isn't specific either. For any number that I start with, I can get to an end number in 2 ways. That's not random. These guys are connected. These guys are very specific pairs of numbers. And what I can observe with enough examples was the relationship between 8 and 4. 8 plus 4 is 12, which is the size of the circle. 6 plus 6 is 12, which is the size of the circle. Now, of course, these examples are quite limited. I should technically change my circle size. But with enough examples, I'm going to see that this happens every single time. Pick another size circle, do this again. The number I add, the number I subtract, those guys are connected in a very specific way that they add up to the size of the circle, which is, of course, equivalent to 0, right? This is equivalent to 0 because on my mod circle, the number, let's say the amount of ticks there are, the amount of representatives of numbers is the same as the position. 12 is sitting behind this 0. 0 is the representative of 12. Okay. So in general, regardless of the circle, mod n, let's pick a number. It doesn't have to be 12. I now want to be general and say, well, for any a integer on the circle, there exists another number, another number, could be the same, but it is another number on the circle, let's call it b, such that a plus b is 0 mod n. And of course, technically speaking, I don't want to get into all the detail there is, but there is a standard property in these that it doesn't matter how I add them, right? I could have said here 8 plus 4, 4 plus 8, doesn't matter. I can swap them around at any stage as I wish. So now this is always happening. So let's give it a name. We call b, this other number, the additive inverse of a. And of course we have to say the circle size, because if I take a different circle, then 8 plus 4 is not going to be 0 anymore. If I take a smaller circle, then everything changes. The connection between numbers change, everything changes. So I do have to specify what I am, what circle I am on. And again, this is just to give you a taste of how things actually sit in terms of understanding, where I am probably going to teach, what is in truth behind the scenes, and where I need to be comfortable in order to make my teaching more effective. I should never teach examples in an attempt to lead students to a conclusion when I don't know a little bit more and I can guide them in the right direction. Now, this is a very simple topic, to be fair. But we'll see when it comes to fractions, the same thing comes up, and maybe that's not that simple anymore to many people. Okay, so we have this property here. Okay, and now in general, we call this the additive inverse. So let's just practice that. Let's make a new page for practicing my exercises. I do have some exercises. Additive inverses is something we want to know. So let's just practice that with different circles and different situations. So what I have here is our exercise. 13.3. I have different circle sizes, different numbers. What is the additive inverse of them? So I'll just copy them again here. Exercise 13.3. Number 1. I'm going to write a sentence just for now. Additive inverse. Well, I cannot write very well today. Of 6 mod 13 is the number I have to add to get to 0 on the 13 circle, and 0 is always going to sit in exactly the same place as the circle size. It's the representative of that modulus, so it's going to be equivalent to 13. So when I say I want 6 plus 7, sorry, I already did the answer, 6 plus something to equal 0, I'm really saying, for my own intuitive purposes, 6 plus something equals 13, and therefore it's 7. I sort of revealed it there by accident. Additive inverse. Inverse of, what's the next one here? 8 mod 24. It's really quite simple. Quite simple. I'm taking a simple setup here to just illustrate something else when it comes to teaching. I'm looking for a number. 8 plus something equals 24. It's, of course, 16. 3. So I'm just practicing different... I need to practice writing, apparently. What is happening with my writing today? As soon as I say something other than what I'm writing, things fall apart very quickly. Multitasking is not my best feature. Additive inverse of 4 on the 9 circle, mod 9, is going to be a 5, because 4 plus 5 is 9, which is equivalent to 0 on the circle. So I am following this situation. Now this on the number line is equivalent to saying a plus b equals n, but not on the circle, right? So there's a difference between writing the representative and actually thinking what's happening behind the scenes to make the arithmetic easier for me. So I have to just get used to 9 and 0 being equivalent on the circle here. Additive inverse, one more, of 5 mod 8 is hopefully obviously 3. I don't need to draw the circle. I don't need to stand on the position and take 3 steps to verify that I get back to the top, which is where 8 is sitting at 0. I hopefully want to get beyond that as I get more comfortable with this modular arithmetic. Okay, so that's the concept of the additive inverse. Now, We can take this a little bit further. So let's just say, okay, well, it's a little silly when I make general statements to bring in a new symbol, a new letter, B, to indicate a number, represent a number that is so closely related to the original number, A. Because in general, I don't necessarily have the specific ticks and examples on my circle. I don't have a specific number in mind. But I know this other additive inverse number is always there. So for convenience, what often happens is we want, when something's so closely connected to the name of the original, we want the name to be very closely connected to the name of the original as well. So another convenient name for the additive inverse of some number that's called A. Now my sentence doesn't sound very good. Let's say here of. The name of the additive inverse of A is negative A. Now on the number line, put this into context, right? Have perspective here. This is only sounding obvious, perhaps, because you are already super familiar with the number line. But long ago, they didn't know what to call these things. They just knew there were these other numbers. Call them whatever you will. That when I add this guy to 1 on the number line, I get 0. So this is the additive inverse of 1. When I add squiggle 2 to 2, I get 0. It's the additive inverse of 2. Additive inverse of 3. Additive inverse of 4. So they wanted to name them in a way that reminds me visually as well that they are the counterparts of the positive integers. And they decided on this naming convention. So I can go, I should get rid of the number line here. I'll just do this. It's too much erasing. So I can go to my examples and say the additive inverse of 6 now has a general name that I'll call negative 6. Now to emphasize that, this is not a minus sign. This is just a little dash that I call a negative sign. It's not the same as minus. It is 7 when I look at the mod 13 circle. So this naming convention is just to replace the words the additive inverse of. This is replaced by a little line there for convenience, which happens often in math. Additive inverse of 8, that is its general name. On the mod 24 circle, it's represented by 16. Additive inverse of 4, oops, not 9. On the mod 9 circle is represented by 5. Additive inverse of 5 on the mod 8 circle is 3. All right, so let's go back here. So now I know that these guys are additive inverses of each other when I look at this first example. That this now means that if I add by a number, I subtract by its additive inverse, and the result is the same. The result is the same. So let's just take this guy. Now, actually, let's take the bottom guy. It doesn't matter. Doesn't really matter which one I'm working with. This one I see already. So elaborating on this, I can take, 7 plus 3 equals 10 mod 12. 7 minus 9 equals 10. But 9 is the additive inverse of 3. So 9 itself has name -3. Put it in brackets. Do not confuse you with what is the operation and what is the name of the number. That's also 10. Mod 12, of course. So the naming convention then leads me to shortcuts for convenience to say, oh, if I see a plus and I see a negative sign, I can replace, sorry, there's a minus. This is why I'm confused. Sorry. Minus. So adding a number is the same as subtracting its additive inverse. And I can then get used to that so much where I say, oh, two negatives make a positive. That's technically not right. But visually, the naming system that we've decided on makes that easy to do and to forget what is actually the link here. If I do it the other way around, 7 minus 9 equals 10 mod 12. Then I could say if I subtract by an integer, by a number, it's equivalent to adding its additive inverse. Now this is just by example, so we'll write that out here. Adding a number is the same as subtracting its additive inverse. Over here, subtracting a number is the same as adding its additive. I have to say additive inverse because there are actually other inverses as well. In this case, it's a specific kind of inverse, the additive inverse. So in the mathematical sense, when I look at these two, when I subtract by a number, it's really just always equivalent to adding by something else, and that something else is linked by the additive inverse concept. This is a subtraction. There's always an equivalent addition. This is a subtraction. There's always an equivalent addition by just appropriately changing that second number. So mathematically speaking, there is no subtraction because any subtraction concept can be rewritten as an addition. There is, mathematically speaking, no subtraction. Subtraction is an intuitive concept of taking away that we naturally view as different, and then we build it up in our minds as a completely different thing to addition. But when you look at how these things are connected, there is no difference between them. It's not new at all. Subtraction, whenever it's there, it's just addition in disguise. Now, of course, this is by example, right? And who's to say that for another size circle, for another set of numbers, it still works the same way? But with enough examples, of course, I know that this is true in general, and I can use examples to introduce this concept to you, like you would any other mathematical concept with numbers or whatever. You would start at this basic left side. So let's just have a taste for how this could look in general. Now I'm going to shorten this a little bit. Actually, I want to get rid of this. I don't like the look of this. I'm going to shorten this a little bit and skip some technicalities here. Is this good enough? Yeah, pen size is okay. So just in general, I'll give you an idea here. What I want to show, right, for this specific example, is that if I can do either one of these. If I subtract, let's do the second one, it's a little cleaner. If I subtract a number, it is the same as adding its multiplicative inverse. Sorry, it's additive inverse. Sorry, I'm getting ahead of myself here with fractions. So we want to show, sometimes it's very nice to start by saying, what would I like to do here? And then let's try and do it. That for any numbers, my writing is just not great. I apologize. Numbers. Let's say we call this guy, let's call it some other number here, right? I don't know. Big N, doesn't matter. And let's call this guy A. Numbers N, A, and little n, of course, my modulars. We want to show that if I take that number and I subtract A, it's the same as taking the number and adding the additive inverse of A. Doesn't matter what the mod is, right? I always know that exists. A has a very long tail here. I don't know why. Okay, so this is what we want to show. I haven't shown it yet. Okay, so now let's do it. In a shortened way, but still. So I start with the left-hand side, and I eventually want to get to the right-hand side. So what we could do, there are some properties that I didn't list, but they're fairly obvious. I'm going to add 0. And in that way, I haven't changed anything. Adding 0 does nothing. But now I'm going to use the fact that 0 is what I get when I add a number to its additive inverse. I called it B, but we've now updated the name to negative A. So A plus negative A is always going to be 0. That's the definition of the additive inverse. So I'm going to write this 0 in a very fancy way as A plus negative A. Now technically there are brackets here, which then I need a property called the associative property to pair other things with each other instead of in this bracket. But we're going to sidestep all of those little technical things. When I add and subtract, it doesn't matter the order in which I pair them up systematically, right? So I'm going to instead group the middle two terms together, because when I have an A and then I take A away, I get nothing. And then what I'm left with is exactly what I wanted to show. Now, I am doing an abbreviated version of this, but just to give you an idea that there is no substantial difference in the subject between examples suggesting patterns and links between numbers and links between addition and subtraction and all kinds of stuff, and proving things in general, regardless of the size of the circle, regardless of the number in question. Subtraction is always equivalent to addition by the additive inverse of that second number. This is completely general. Now, of course, me as a teacher, I've done all these things, all the proofs in detail, in general, deductive reasoning. I know that when I set up examples, I'm leading you to the correct conclusion. Where is my... to the correct conclusion. Even though you might never see those deductive reasoning arguments laid out. You might never need to see it if you are a student. On the left, just getting an introduction. But as a teacher, I need to know a little bit more so that I can set up examples and guide you in the right way, in the right direction that I know is true. The same goes when you sit in front of little Timmy. You're not going to do sophisticated arguments and general deductive reasoning. It's very unlikely. But you need to know the direction in which you want those examples to lead him to make conclusions, so you know those conclusions are correct. So we have to know a little bit more and understand where we are on this line. That I might be teaching on the left, but I need to know a little bit more. And when things get complicated, those options are there to drift over in the understanding spectrum, as I need to still be efficient. This was just one little topic to raise awareness of this situation when it comes to teaching, whether it's me teaching you or you one day teaching someone else. I want to be aware of this. Where am I in the current discussion? Where should I be in my head, in my understanding, so that the discussion, which is probably on the left here, is done correctly and effectively. And I've just used this modular arithmetic to give you an awareness of this, but it transfers to really anything. If I'm teaching essay writing in English or whatever language, I need to know way more about how an essay is constructed, put together, all the pieces, and all those things. Even though I don't necessarily say it, I use that knowledge to guide them into better writing their essays. So it's not all just about math, it's more about teaching sometimes. All right, that is the end for today. Any thoughts, comments, criticisms, compliments? No. Understanding that tomorrow is a holiday. So you should feel pretty good. And this topic isn't super complicated. In terms of test questions, you just have to be able to do a basic calculation, mod something, and maybe find what is an additive inverse of a number. And in terms of testing, there isn't that much we could do, right? But in terms of a discussion that it gives an opportunity for, I feel that there was a little bit more. So there's a difference between what we talk about sometimes and specific test questions, but they're still all good and important things. Well, I hope you enjoy the holiday tomorrow and take a look at the schedule to know what is coming up, and we will continue when we continue. Until then.
Please remember to click the like button if you enjoyed the video and to subscribe if you want to be notified of more videos.